Welcome back. This is part 3 of lecture 3. We shall talk about the last proposition of book 1, I believe. That is proposition 147 and is nothing other than the Pythagorean theorem. I'll state it and then we start proving it. Okay, so that's proposition 147, otherwise known as the Pythagorean theorem. Okay. It says the following. In a right triangle, the square of the hypotenuse is equal to the sum of the squares of the sides. Is equal to the sum of the squares of the sides. So I'll draw the picture as I go along with the proof on the side, and then I'll write the proof. I'll write the proof here. So the first thing we do, we start with a arbitrary triangle, ABC. Start with an arbitrary triangle ABC. Let me draw that. Okay. This is some right triangle though. So this is the right angle. So A, B, C. That is my right triangle ABC. By proposition 146 of part 2, it is possible to construct squares on the three sides of this triangle. So I'll write here, by proposition 146, construct squares on the three sides. Okay, so I'll do that. Let's see. Okay. This is one of the squares. So Surely it's not perfect, but will do. And here, I'm trying the other one. So these are the three triangles that are, not triangles, squares that are built on the sides A, B, C respectively. Now, by proposition 131, I think, 132 rather, or not so sure I remember, 131 or 132, we can show that, we'll draw some lines now. I will draw the line AL. I'm going to call this AL. Let me call this L. By the way, while I'm here, let me just actually name all the corners of all these squares before we move on. So let me call this E. Let me call this D. Let me call this F. Let me call this G. Let me call this K. And let me call this H. Okay, I think I named them all. So I'm going to draw the line AL. And by proposition 131, we can show that, so by proposition 131, it's possible to show that the line AL is parallel, line AL is parallel to the line BD. Parallel to the line BD. So that's what we are going to show. So first thing we do, we draw the line AD and FC. So draw AD and FC. Line AD is here. So I connect A with D. And line FC on this other line here. Okay, line AD and line FC. Note the following. Note that the angle GAB is a right angle because I built a square on the top of the line AB. So note that angle GAB is a right angle. Is a right angle by construction. Is a right angle by construction. Okay? And also BAC is right. That's also given. No? BAC is also right. And BAC, angle BAC is also right because we have a right triangle at A. And BAC is also right. This is given. Okay. So we have angle GAB and angle BAC to be equal to two right angles. So angle GAB plus angle BAC is equal to two right angles. Okay. And by proposition 114, this means that the line GAC, this line GAC, is a straight line. And then by proposition 114, line GAC is straight. It's a straight line. Straight line. Okay. So now I'm going to consider two triangles. So now consider triangle ABD, triangle ABD. Perhaps I should A B D. So I'm going to consider triangle ABD and triangle BFC. BFC. I'm going to draw that with a different BFC, so it's actually a bit more visible. Let's say blue. Yep, it's blue. Okay. So BFC. So I'm considering the red and green one. I'm going to consider these two triangles. Okay. Now let's see what I have. In triangle AB, the line AB, in triangle ABD, the red line AB, it is surely equal to line FB in the green one, or BF in the green one. Why? Because they are both sides of the very same square. So that is by construction. By construction. These are sides of the square ABFG. Okay, so this one, the line BD in the red triangle is also equal to the line BC in the green triangle, also by construction, since they are lines of the very same square, namely square BCDE, so they are sides of the same square. Further, let me talk about some angles now. I have angle FBC, this large angle here, FBC. The angle FBC, it is equal to what? It is equal to angle FBA plus ABC. So it is equal to FBA, I repeat, FBA plus ABC plus angle ABC. Further, the angle ABD, this other large angle, ABD, the angle ABD is equal to what? Is equal to angle DBC, angle DBC, plus what? Plus angle ABC. So the large red one is equal to DBC plus ABC plus ABC. Now, so this means that the angle, not this means, by angle FBA is what? Is a right angle. And also angle DBC is also a right angle, no? So the angle FBA by construction is right, and so is the angle DBC. These are two right angles, okay? And they are equal to one another. So since FBA is equal to DBC, any two right angles are equal to one another. This is by one of the postulates. Then this angle is the same, so these two angles are equal to one another. These two are the same angles, so by common notion 2, these two other angles must be equal to one another. Then by common notion 2, we have angle FBC to be equal to the angle ABD. I'm simply looking at this system of these two statements. So ABC is the same. These two are equal to one another because they are right angles. Therefore, by common notion 2, these two are equal. If equals are added to equals, what comes up is still something equal to the other one. Okay. So this means that hence what? Hence triangle ABD is congruent to triangle BFC. That's what we were considering to begin with. We were considering these two triangles, and these two triangles will be congruent by what scheme actually? Would be side angle side. Okay, are congruent by side angle side. Congruent scheme. And therefore they have the same areas. And since they are congruent, they have the same area, and they have the same areas. Okay, now consider two other triangles. Consider further these two other triangles. Triangle ABD, triangle ABD, still the right triangle, and BD, this point here, let me call it ML. So I'm going to consider triangle, the red triangle, this red triangle here, and this other rectangle. I'm going to mark that rectangle blue. So this is the rectangle. So red triangle and blue rectangle. Okay? And rectangle, this is for rectangle B, D, M, L. Okay, what do they have in common? Do they have anything in common as shapes? They actually do. They have the line BD. You see the line BD is red and blue at the same time. So the line BD is common. That means is common to both. That's what this notation means. Okay. Now, do these figures fall on the same parallels? Yes, they do. BDLM is a parallelogram, and ABD is the red triangle, and they both fall on these two parallels. Parallel BD with AL. We said from the very beginning that AL is parallel to BD. It's possible to show by this proposition that they are parallel. So, okay. So, both shapes fall in the same parallels. Parallel lines AL and BD. We said that from the very beginning. So by proposition 41, which I mentioned in part 2, so by proposition 41, it means that the area of this rectangle, which is at the same time a parallelogram, is twice the area of this red triangle. So by proposition 41, area of BDML, which is the blue rectangle, it is equal twice the area of the red triangle ABD. Area of triangle ABD. Similarly, we show the following. Similarly, I'm not going to draw more lines because it actually adds a lot to the picture, but similarly, we show the following. Rectangle, area of the rectangle A, B, F, G, A, B, F, G is equal to twice, it is equal to twice the, let me see if I have that right, A, B, F, G is twice the area of triangle ABD for the very same reason. Why? Because remember the line GAC is a straight line. So they both fall in the same parallels, no? Okay, so let me just write that. So similarly, area ABFG, for the very same reasons by proposition 41, is equal to twice the area of triangle FBC. FBC. So I'm considering in when I say similarly here, I'm talking about the green triangle with this square. They fall on the same parallels. Keep in mind the line GAC is a straight line. I said that in the very beginning by proposition 114. So this is a straight line, this is a square, so the lines are parallel, and you have this square and this green triangle lying on the same parallels and having the very same base, the base BF. So by proposition 41, the square ABFG is twice the area of the green triangle. That's what I mean by similarly. Remember that JAC, not J, but GAC is a straight line. Okay. Okay. Now, we have a following. So what we have said so far. Area of BDML. BDML is the blue rectangle. Area of BDML. We said that it is equal to twice the area of triangle, ABD. Okay. So this is the same triangle ABD. That would be equal to 2 times the area of triangle FBC. Why? Because that is equal to area of ABFG. ABFG. So this is true from here, and this is true from the other one. Now, let me take a minute to make sure that I have everything correct. ABD, FBC, and that's the square ABFG. Okay. Now, I'm not, well, by drawing the following lines, if I connect this line meaning the line AE and BK, and do the very same thing, the very same line of reasoning, but with these two instead of these two, I can similarly prove that the following are equal. So let me just write this by drawing AE and BK. Similarly, it's proven that area of MCLE, this other, I'm not gonna add more colors, just try to follow the notation. Area of MCLE LE is equal to area of CKH. CKH. Triangle CKH. No, I'm sorry. Square ACKH. Area of the square ACKH. Okay, where does it get us? I'll try to write at the end. Finally, what is it that we have? Finally, we have this. Area BCDE, BCDE, which is one of the squares. So area BCDE, that is a square. This area, it is equal to what? It is equal to the blue triangle and this other, not triangle, blue rectangle and this other uncolored rectangle. So the square BCDE is equal to the area BDML, the blue one, BDML, plus the uncolored rectangle MCLE, plus area MCLE. It is this other uncolored rectangle. And both of these rectangles we showed from the steps before are equal to, so we just showed that the blue rectangle is the same as the area of this square here. And by the similar argument we showed in the previous step that this rectangle here is equal to the area of this other square right here, and then we're done. So BDML, the blue one, is equal to the area of this smaller square, and that square is ABFG, plus this other one here, this other uncolored rectangle, is equal to the area of this square. So area of the square ACHK. And that actually concludes the proof. You're showing that the square of a hypotenuse, which is the same as the area of this square, is equal to the sum of the squares of the sides, which is the same as saying is equal to the sum of the areas of these two squares here. And then we are actually done with the proof. Okay, I'm just going to state here proposition 48. Proposition 48 is nothing other than the converse of the Pythagorean theorem. I'm not going to prove it. So proposition 148. Okay, and that is just the converse of 147. It says the following: in a triangle, if the square on one side, if the square on one of the sides, if the square on one of the sides is equal to the sum, is equal to the sum of the squares on the remaining sides, is equal to the sum of the squares on the remaining sides, contained by the remaining sides is right. The angle, or that's the same as saying the triangle is a right triangle. So the angle contained by the remaining two sides is right. It's not too difficult to prove it. I think the proof is in the book and it's a nice proof. Now that would be the end of lecture 3. Together with this video comprised of 3 parts, I'm going to also post some problems, and they all have to do with the Pythagorean theorem. There are so many different proofs of Pythagorean theorem, some a lot easier than others, so that portion of the homework deals with exactly that. It gives you some outlines as to how to prove the Pythagorean theorem differently. And it will be nice to see what you guys can do. As always, feel free to talk to me on Blackboard whenever we meet. Thanks everyone, and you'll hear from me next time.